Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Cybono Discovery Center. Right, good people, you would recall last week we did some revision of trigonometric concepts, which are very, very important and would be applied in grade 12. So we thoroughly revised grade 11 work. So today we are going to do the first part of the grade 12 work on compound angles as well as on double angles. Please remember, we are also available on WhatsApp. Our interactive number is 064-748-8913, 064-748-8913. It will keep popping at the bottom of your screen. Please do ask questions about the lesson that we are having today. Do ask those questions so that we can be able to assist you. Right, obviously we would have our lesson objectives, and the objectives for today is by the end of this particular lesson you should be able to understand the summary of all trigonometric theory that you learned in grade 11, should be able to derive and apply the formulae for compound angles, should be able to expand that knowledge of that particular formula and use it to derive the other formulas. That would be the cosine of a plus b, the sine of a minus b, and the sine of a plus b. So you should be using that one formula to get the other formulas there, to get a full complement of the compound angle formulas, which are 4. So you're going to derive one and then you use the 3. You use that one to derive the next 3 there. So we solve simple problems using compound angle formulae. We also use compound angles to derive formulae for double angles, and then from there we solve problems requiring the use of Pythagoras theorem, without the use of a calculator. We also solve problems requiring the use of reduction formula, and then as well as prove identities, right? Obviously this is on page 42 of your CAPS document and on page 8 of the exam guideline that was published in 2021, right? The knowledge that you should be bringing into this lesson is basically the concepts that we looked at last week. Those concepts would be the definition of trig ratios in a right-angled triangle, and a definition of trig ratios in a Cartesian plane. You know, in a right-angled triangle, we'll define the sine of an angle theta. If you have a right-angled triangle like that, and we have theta here, and then we say this is the opposite side to theta, and this would be the adjacent side to theta, and then this would be the hypotenuse side to theta. So you define sine as opposite over hypotenuse, the cosine as adjacent over hypotenuse, and the sine of that particular angle theta is opposite over adjacent. That's how you describe them in a right-angled triangle. So it's just the recall, that the pre-knowledge that you need to bring, and also you know you can define them in a Cartesian plane, where now you are going to say sine of theta being the opposite is y, the hypotenuse is r, because the x, the y, as well as the r, when you're defining that using the Cartesian plane. And then from there, reduction formulae, cofunctions, negative angles superior than 360, special angles, and basic trigonometric identities. Those are the things you should be bringing into this lesson, and those are the things that we did last week, right? Now let's look at the summary of grade 11 concepts that you need to know. Obviously we looked at that also last week. This is the trig theory there. You see that now we divide that into the 4 quadrants, and in quad 1 we get that we know that all of them are positive. Sine is positive, tan is positive, and the cosine is positive. But when you move to the second quadrant, you can see that now only sine is positive. Only sine is positive. The rest of the trigonometric ratios are negative. In the third quadrant, you get to see that only tan is positive and the rest are negative. In the fourth quadrant, you get to see that only the cosine is positive. The rest are actually negative there. And with the reduction rules, we know that when we have 90 minus, sine changes to cos at 90, and cos changes to sine there. So this would be cos theta, and then cos 90 minus, that would give us sine theta, like that. That's what we dealt with last week. We also know the reduction in terms of 180. You check the quadrant. If they say 180 minus, when you locate the quadrant, you know that should be in quadrant 2, and you get to see that the sine is positive in quadrant 2. That is why we are obtaining the positive sine theta. And then from there, if it's at the tangent of 180 minus, you locate where 180 minus is obviously in the second quadrant, and tan is negative in that quadrant. That is why here we have negative tan theta, like that. So it goes on and on, the reduction rules that we looked at. So this is just the summary of what we did last week. Now we need to also zoom into the concept of negative angles. When we explain that concept, we refer to the negative angle as an angle that is in the fourth quadrant, because if you are to go here anti-clockwise, and in the same, you move the same direction in the opposite direction there, or you move the same particular angle, you move at the same angle but in an opposite direction, you'll get that the negative angle here would be in the fourth quadrant, and in the fourth quadrant it's only cosine that is positive. That is why the cosine of the negative angle would become positive there, because the cosine is positive in the fourth quadrant and the negative angle is actually in the fourth quadrant. So now identities, obviously, but before we get into identities, I would need to also make you aware of the fact that we are using reduction. It is called the reduction formula simply because you are taking angles that are not necessarily in the first quadrant, that are not acute. You are taking angles that are not acute and you are making them acute angles. So you are reducing. It's an angle that is either obtuse, reflex. You are trying to then say, let this angle be acute. So that is the aim of reduction, is to reduce angles from being angles that are greater than 90 to being angles that are less than 90, or to make them acute. So we have to reduce them, and hence the reduction formula. Right, we get into the identities. We know that the cosine squared of theta plus the sine squared of theta is 1. We worked a lot with that last week. You also have that the tangent of theta should be the sine of theta divided by the cosine of theta, like that. Right, obviously we can also speak to multiple angles, and with multiple rotation we said that if you get angles that are greater than 360, you're going to subtract 360 until you get angles that are less than 360. Then you can apply your normal reduction formula, like that. Right, let us now look at the new concept, the grade 12 concept. That is the concept of the derivation of the compound angle formula. The compound angle formula. So we are going to be looking at this one. We are deriving the compound angle formula for a minus b. Why are we saying the angle is compound? If you look at this, it is made up of two different angles. Two different angles, with one being a and the other one being b. But because of that, because it's the addition or the subtraction of two different angles, we say that this is the compound angle. It's the compound angle. Now we're going to be using this derivation. Remember, the derivation, you should note that the derivation is not examinable. The derivation is not examinable. So you are not going to be actually examined or tested on the derivation itself, but we're just going to show you just how it is derived. So simply here, what we basically do is we are going to have that we draw two terminal rays from the origin, with the same length r, like that, and then we have an angle of elevation here to the first ray. We call that angle alpha, and then we have another angle of elevation there to the second terminal ray. We call that angle beta. So that is the first step. And then from there, if we are to join the two, we are forming a triangle, and we want to find this interior angle of that particular triangle, which is an angle made up of, if you check that angle, it is an angle made up of alpha as well as beta, like that. So if you check, this particular angle is the one that we want. So that angle plus alpha gives you beta, which means that particular angle will then be given by beta minus alpha, and hence the beta minus alpha that you have there. And then from there, we are going to use our knowledge of trigonometry to actually work out the cosine of alpha. If we work out the cosine of alpha, it would be the adjacent side x over the hypotenuse, which is r, which means that x would be given by r, the cosine of alpha. And you can do the same for sine of alpha. It would be y over the hypotenuse r, which means that y will then be equals to r sine of alpha, like that. So that is how now you are going to get the coordinates of point B. R cos alpha, R sin alpha. You do the same with the coordinates of point A by looking at this particular angle there, and then you'd be able to work that one out. Now, once you have those coordinates, you are then going to make use of two formulas. One formula, you take that from the cosine rule. You use the cosine rule here with respect to this particular angle beta minus alpha, and this is what you are going to actually obtain from using the cosine rule. And then similarly, you can still or conversely, you can still use also the distance formula to find the length of AB squared. So this length of AB squared can be found using the cosine rule. It can also be found using the distance formula because you have those coordinates. And then from there, you are going to equate the two distances, the one that you worked out using the distance formula and the one that you worked out using the cosine rule. And then from there, you are going to then simplify that. Ultimately, it will land you here. It will land you where now you get that the cosine of beta minus alpha is equals to the cosine of beta times the cosine of alpha plus the sine of beta, the sine times the sine of alpha, like that. So the derivation is important for you to know, but it is not examinable. Please just look at it. Just look at it. What is important is the application thereof of that particular derivation, right? Now, let us look at now the application. We are now starting with the application, but before we do the application, we are going to now learn how to derive, because there are 4 compound angle formulae, and here we just derived one. So we are going to use the fact that this one is true to then derive the other formulas, which is now, this part now here, it is very much examinable. It is examinable to use an existing formula that has been derived to derive the rest. So that is very, very important, and you have to know how to do it. It's been tested before in past exams, and it can be tested in future exams as well. It's a skill that you need to acquire. Right, let's look at this one. The first one now, the solution. Let's look at what the question demands of us. The question says use. You see, we are going to use this existing formula. It's the one that we derived. We're going to use it to derive a formula for the cosine of A plus B. So now, which means that we have to change this compound angle. You see, the compound angle of the formula that we know is A minus B. But the compound angle of the formula that we need is A plus B. So how can we make this look like that? We need to have a difference between the two angles instead of having the sum between the two angles. So to achieve that, we are going to do this. The cosine of A plus B, it would be equals to the cosine of A minus negative B, like that. Now, if you look at this, A minus negative B, what will it give us? A plus B. It is taking us back there. So what we are doing is we are trying to write it, or to express the compound angle A plus B as a compound angle A minus instead of having A plus, because the formula that we know has A minus B. It has a negative, or it is subtracting the two angles, but the one that we need is adding the two angles. So it is best that we now make sure that we have a negative like that. So we can just take out a negative like that, and then mathematically it would be negative B. So now you have the difference between two angles. What are those angles? A and negative B. It is like this one, where you had a difference between two angles, where the first angle is A and the second angle is B. Now we can use that one. It is saying now, if you have cos A minus B, you would have cos A cos B. So it's the cosine of the first angle times the cosine of this second angle, which is negative b, and then you add. So you see, if this sign is negative, there is a change of sign here. So we're going to add the sine of the first angle times the sine of the second angle, negative b, like that. So now what we are going to do is now simplify this using our knowledge of the negative angles that we studied in earlier grade. So this would be the cosine of A. Remember, a negative angle is in the fourth quadrant. All negative angles are in the fourth quadrant, because if you are to go theta, same angle, negative theta, and only cosine is positive in the fourth quadrant. So this would be cos A cos B. This cosine of B would be positive, plus sine A, but now you have negative B, and negative B is in the fourth quadrant, and sine in the fourth quadrant is negative, because all of them are positive in the first, sine is positive in the second, tan is positive in the third, and cos is positive on the fourth quadrant. So sine would be negative, so this would be negative sine beta. So now if you simplify this, you get that this is cosine A cosine B minus sine A sine B, like that. So that is how we are going to derive the formula for the cosine of A plus B using the existing cosine of A minus B that we derived. Right, now let's move on. We can derive the rest of the formulas using, remember, we are using the cosine of A minus B, which is the cosine of A times the cosine of B plus the sine of A times the sine of B. Now we can use that to actually derive formulas for the sine of A plus B. How can we do that? We express the sine of A plus B as the cosine of 90 minus. Remember, we said if you have the sine of, or the cosine of 90 minus theta, this changes to sine theta. So we can write this a sine as a cosine provided the angle becomes 90 minus the original angle. So we also wrote down here the sine of A plus B, we expressed it as a cos, so it should be the cosine of what? 90 minus the given angle, so it's 90 minus A plus B. Simplifying that, we get the cosine of 90 minus A minus B, and then from there we are going to expand using the formula that we know, and ultimately we end up with the sine of A plus B, which is the sine of A, the cosine of B, plus the cosine of A times the sine of B. Similarly, you can do the same also to derive the formula for the sine of A minus B. Remember, if you want to write the sine as a cosine, why are we writing it as a cosine? We are writing it as a cosine because the original formula was given in terms of the cosine. So this in order for you to write down the sine as a cosine, you should, the sine of an angle as the cosine of an angle, you should then say the sine of that particular angle would be the cosine of 90 minus that particular angle, because sine and cos are complementary functions, they complement each other, so they have that property. Now obviously we say now sine of 90 minus, then we manipulate this such that this should be a negative sign, and then we expand the cos of 90 minus A, the cos of negative B, and then the sine of 90 minus A, the sine of negative B. Cos 90 minus A changes to sine A, and then cos negative B remains positive cos B, because the cosine is negative is positive in the fourth quadrant, and then the sine becomes the cosine, and then the sine of negative B becomes negative sine B. That is why the sign is now negative as opposed to being positive, like that. So we've derived the other formulas. Now the summary thereof of the formulae This is the summary of the formula that is being used, and it is available in your formula sheet. So please make sure that you familiarize yourself with the formula sheet. The formula sheet should be your friend, especially when it comes to trigonometry. It should be your friend. So these formulas here, you can see that this is the one that we originally derived. So the cosine, you'll see that the cosine expansion, if it's cos alpha minus beta, what happens is that the sign here becomes opposite to what you had. Also check cosine plus here, but there it's negative. So the sign becomes opposite to what we have. And then to expand that, if it's a cosine, you'd go cos of the first angle times cos of the second angle, and then you change the sign, and then you put that the sine of the first angle and the sine of the second angle. But when you expand the sign, the sign there remains the same. Negative here, also negative there. So you get that the sign is preserved. The sign there is preserved. And then how do you expand? It would be the sine of the first angle, the cosine of the second angle, plus the cosine of the first angle, the sine of the second angle. So that is very, very important. Please make sure you familiarize yourself with these formulas. They will be given to you in the formula sheet when you write your tests and also your exams. So even when you write your classworks and your homeworks, make sure that you have that formula sheet handy and you make full use of it. Right, now let us look at the approach to questions. How do I approach trigonometric questions? One, I need to read and understand the question scenario. That's very, very important. Number two, we can use a diagram if the question instructs, or if it's a question that needs a diagram. And if the diagram is given, it's important to know how to analyze. But if it's not given, it is important to know how to sketch it where applicable. Right, now step 3, you interpret the questions extracting key information. That's very, very important. Key information should always be extracted from those questions. Step number 4, select the correct. You see, select, not memorize the correct. Select the correct formula or identity and substitute correctly by performing some arithmetic calculations without the use of a calculator where applicable. Step 5, one must answer the question and remember to conclude at the end. If they say prove an identity, at the end you should conclude that indeed the left hand side was found to be the same as the right hand side. It's important to conclude, answer what is asked. Right, now step 6, often in trigonometry we have questions that follow on. It's called scaffolding. That is where the answer to the previous question is needed for you to actually come up with the answer to the next question. So it's very, very important for one to look out for that. And at times it is things that have been proved above. Look at utilizing them when you solve the next questions. Right, now let us look at the application. The first part of the application is the use of the compound angles to solve problems. So we are exclusively using compound angles here to try and solve, which means our knowledge to expand here would be tested. Now, if we check, we are expanding sine. How do we know it's a compound angle? It's alpha plus what? Plus 45 degrees. Good people, please look out for this one as well. When they say 180 degrees plus alpha. You see, this is a compound angle. This is a compound angle. It meets all the conditions of being called a compound angle. But remember, once you start getting 180 plus, that compound angle can be reduced without making use of the compound angle formula. It can be reduced making use of what? The reduction formula. Very, very important. That is key. Be able to separate between what you call expressions that can be simplified using reduction formulae, and expressions that should be simplified using compound angle formulae. Because the compound angle formula is the general approach of how to simplify this. But remember, you also have knowledge of reduction formula. Those that need reduction, 180 plus, 180 minus, 90 minus, 90 plus, all of those, they need you to use earlier grade knowledge of what? A reduction formulae. But these ones here, because they are not defined as standard angles in the Cartesian plane, you know, this is 0, this is 90, this is 180, this is 270, and you are coming back here at 360. So all these angles here, if you want to reduce, given these angles there, then you make use of what? The reduction formula. But now here, if you want to simplify, 45 is not part of the standard angles in the Cartesian plane. So in order for you to simplify that one, we need to make use of the compound angle formula. I hope that is well captured. Right, now we move on. Now, if you look at this now, we can look at the general form. We know it's alpha plus beta, which we looked at in the previous slide as sine of alpha, the cosine of beta, plus the cosine of alpha, the sine of beta, like that. So that is how we said, if we look at this, can basically look at this here, that is how we said we are going to simplify, or rather to expand for what? For the sine. So it's in the formula sheet. So this here that I'm using, quickly going back there, allow this to pass. Right, and then you see this is the formula that is in the formula sheet. Now, let's check how we can use it. The first angle is alpha, the second angle is 45. So it should be the sine of alpha plus 45 now should be the sine of alpha, yes, the cosine of 45, because the second angle is 45, plus you maintain the sine, the cosine of alpha, indeed, sine of the second angle, which is 45. Now you've expanded that one, but you get to see that, oh, but I have these special angles. I know 45 is a special angle, so I can further simplify this one. So this would be the sine of alpha. Cosine 45 would be the square root of 2 over 2. You use your calculator to simplify that one. Plus the cosine of alpha times, it's a special angle. Remember, our calculators nowadays have special angles, but those of you that are still using the triangles and the unit circles to find special angles, you can still do so. So this would be root 2 over 2, like that. So now to simplify this, you can see that root 2 over 2 is a common factor. So I would factor out root 2 over 2. This would be sine alpha plus cos alpha, like that. So you have just simplified this one using the compound angles. Right, we move on. Now we are still using the compound angle formula. Now, good people, it's very, very important for you to note that these formulas, these expansion formulas, they work in both directions. You should be able to move from left to right and expand, and also to move from right to left and congest. So the congestion is also true. So here, if we look at this one, it's cos, cos, sine, sine. And we know the compound angle that takes cos multiplied by cos, sine multiplied by sine, should be the compound angle for the cosine. So if it's the cosine of alpha minus beta, it should be the cosine of alpha, the cosine of beta, plus the sine of alpha, the sine of beta, as per the formula sheet. If it's the cosine of alpha plus beta, it should be the cosine of alpha, the cosine of beta, minus the sine of alpha, the sine of beta. You see that the sign changes. Now, we check this one. This one is cos minus sine. Because it's minus sine, it is the second formula. We can now move from right to left. In the previous one, look at this one. Look at this one. In this one, we were moving with our formula from left to right. But the same formula applies also from right to left. If it is in expanded form, we can be able to congest it. If it is in compound angle form, we can be able to expand it. So it's very, very important. It's very, very important. It's key. You will see as we go on with our examples that would be expanding as well as congesting there. So the first one, you can see that now obviously this should be the cosine of the first angle x minus or plus the second angle y, like that. So this would be how you congest it, because you see here it was cos minus sine. If it's cos minus sine, it should be the cosine of the first angle, which was x, plus the second angle, which is y, like that. So the second one, number 1, it's sine 20 cos 40 cos 20 sine 40. So this one is given in the form of sine cos sine. So because it's sine cos and sine and cos alternate, so it's a compound angle for sine and it's positive. So which means that we can look at the sine compound angle alpha plus beta as written in the formula sheet. That would be the sine of alpha, the cosine of beta, plus the cosine of alpha, the sine of beta, like that. So it means that now I should be able to then congest this one. The first angle, you can see your alpha is 20 degrees and your beta is 40 degrees, because this is sine 20 cos 40, right? And then cos 20 sine 40. You can see the trend there. You can see the trend there. So now to congest this one, you can see that the first angle is, so this should be the cosine, or it should be the sine of what? The first angle is alpha, and I should be adding the second angle. Oh no, my bad. Let me do it here. Sine, we said the first angle is alpha, and alpha we said it's 20. The second angle there is 40. The first angle is alpha, beta, alpha, beta. So that's how it's been used in the formula sheet. So you want to associate it with the one that is used in the formula sheet. So now we get to see it's the sum of two angles. That should be 20 plus 40. That should be 60 degrees. So we get that it's the sine of 60, which should be, according to your calculator, sine of 60. It's a special angle. It should be given by root 3 divided by 2. Root 3 divided by 2. So that gives you the answer to that one. Very, very important. So the skill to congest is paramount here. Now let's look at this one. We are still making use of the compound angles to solve without the use of a calculator. You are now given the cosine of 15. And you know, if they say without the use of a calculator, then your answer should be given in what? In fraction form and radical form, like that. You cannot write it as a decimal. So the cosine of 15, now we need a new skill, because this 15 here, it is what we normally refer to as a hidden compound angle. Or this 15 hides compound angles. It's a form that has compound angles in it. Within that 15, there exist compound angles. Now, how do we get those compound angles? We are going to check our special angles. Check any two special angles that can add or subtract to 15, because 15 is a very low number. We know our special angles are 0. Obviously, most ones that we use here will be 30, 45, and 60. These are the mostly used special angles there. So we have 0 and 90 as well as part of these special angles. But now, if we look at this, we need to utilize any of these special angles that can assist us to get what? 15. So if you check here, if I can use the cosine of 45 degrees minus 30. What is 45 minus 30? 45 degrees minus 30 degrees simply gives me 15 degrees. So I've expressed 15 as a difference of what? Two special angles. You can also express it as 60 degrees minus 45 degrees. This is also okay. It's also okay. It's also okay. It's true as well. It will work. But now, for the purpose of time and saving time, thereof, we will just use one of these. We will not use the 60 minus 45. You can use that in your spare time. Just look at it. It will give you the same solution that I will get here, because 60 minus 45 is also 15. So now, because I have two compound angles, or rather I have two angles that are subtracted together, they form what we call a compound angle. I can then use compound angle formulae to expand. So this would be cos 45. I'm using this one because it's cos alpha minus beta. This would be the cosine of alpha, the cosine of beta, plus the sine of alpha, the sine of beta. Right. I'm writing this formula here just to show you how important it is to always refer to the formula sheet. So going on, I wouldn't be writing the formulas back. Remember, you go to the formula sheet, you check the formula. So this would be cos 45. First angle is 45, second angle is, first angle is 45, second angle is 30. First angle is 45, second angle is 30. So this would be the cosine of 45, the cosine of 30, and then the sign that we should use is positive, plus the cosine, the sine of 45, the sine of 30 degrees. So to simplify this, we know cos 45 is root 2 over 2. It's a special angle. Cos 30 is a half. It's a special angle. Sine 45 is root 2 over 2. Sine 30 is root 3 over 2. Right? We can just confirm those using our calculators there, just to make sure that we are having the right thing. Sine 30 should be half. Sine 30 here should be half. Cos 30, that is the one that is root 3 over 2. So that is why I was saying it was important to confirm using our calculators there. So now if we multiply here, I have numerators is root 2 times root 3. I can get that this is 2 times 3. If I multiply two radicals of the same degree, then I can multiply the numbers or the radicands. So this would be 6. So this would be the square root of 6 divided by 2 plus square root 2 times 1. That would be the square root of 2 divided by 4. Divide by 4 like that. So I can take 4 as a common denominator, then I can add the numerator, square root 6 plus square root 2, like that. So that is how you will then be expressing what? The cosine of 15. Therefore, the cosine of 15 without the use of a calculator can be written like that. Remember I said when they say without the use of a calculator, they are not saying you should not touch the machine at all. They are just saying your answers should not be given in decimal form. They should rather be given as a fraction, or also include what we call now the radicals, the roots. Right, we move on to example 5. Now, we are still using compound angles, but now we need to be smart about this one. Remember, we started this side. We said here, okay. Here we said, okay, we should also be able, we just go slightly backwards. We should be able to move forward and do what? And expand. In the next one, we're testing whether we are able to go back and congest. In the third one, we are saying, will we be able to expand if the angle there infuses special angles, but those special angles are not explicit? You first need to be able to work them out because they are not explicitly given. So you need to go and get the angles that can give you 15. And we were expanding. Now, we are on this one. This one we are given now half. We are given now √3/2. These are now what we call what? We call these ones the special ratios. Where do we find special ratios? Sine 30, sine 45, cos 60. What are the special ratios? Sine 30, if you check sine 30 and you get half. Cos 60 you get half. Sine 45 you get √2/2. Sine 60 you get √3/2. So all these answers that you are getting, because these answers are from special angles, they are special ratios. So you need to be able to pick them up in a question to say, oh, but this is a special ratio. It might happen that they want me to bring back the corresponding special angle. Very, very important. When given the special ratio, you get the corresponding special angle. But when given the special angle, you get the corresponding special ratio to simplify. But now to simplify here, you are given special ratios, so you should be going back to the corresponding special angles. Now, how are we going to do that one? Look at the solution to number 1. We have half the cosine of x. I can write half as what? As the cosine or as the sine. I'm allowed. I can write it as the cosine of what? It should be the cosine of 60. Cosine 60 is half. And then I would have the cosine of x. How can you get it? If you want to write it as a cosine, you can take in your calculator the arc cosine of half to give you 60. Tells you that you should be using the cosine of 60. Now, plus, I know now that I've written this as cos, which means that in order for me to be able to congest, the next part should be written as sine of an angle times what? The sine of an angle, x there. So, which angle can I have? √3/2. It's the sine of what? The sine of 60, like that. So you see, I have changed the special ratios and now I'm writing them as the special angles. The special ratios have now been written as a special angles. Now, since you have this one now, you can be able to congest. Cos, sine. So this is a compound angle for cos. This should be the cosine of 60. Because the sign there is positive, it should be minus x, like that. So you were able to express, because the question said express as a single trigonometric ratio. Alternatively, as I said, let us look at the alternative approach quickly. Alternatively, as I said, you can be able to also decide, or you can decide to say, but half can also be a special ratio for the sine. So I can write it as the sine of 30, the cosine of x, plus, so it's sine cos, which means that I should now have cos sine. So I will write root 3 over 2 as the cosine of 30 as well, then the sine of x, which means that now I am using the compound angle for sine. This would be the sine of what? 30 degrees plus x, like that. These two are the same. The answers there are the same. One would think that they are not, but if you can check, if you check the angles, they should give you 90, and we know that the cosine and the sine are complementing each other at 90 degrees. Right, now the second one is root 2 over 2 into the cosine of x plus the sine of x. Similar approach. So I would want you to actually try this one out. I will give you just 3 minutes. I want to give you 3 minutes just to try this one out and see whether you'll be able to do it just like I did the previous one. So you just have 3 minutes to quickly respond to Roman figure 2, and your 3 minutes start now. Right, hello and welcome back. Now let's see whether you were able to actually use your brains to actually work this one out. It's not a difficult one, so to say, but it's just a bit different from the one that we did first. So now what I'm going to do first is I am going to distribute the square root of 2. So this would be the square root of 2 cosine x plus the square root of 2 sine x. Then from there it's a common denominator 2. So I'll divide each term by the common denominator. That is square root 2 over 2 cos x plus square root 2 over 2 sine x. Now you can see that, oh, I have my special ratios. So you can express these special ratios as cosine or as sine, as you please. So I would just express it as the cosine of 45, the cosine of x, plus the sine of 45, the sine of x. Why am I making this one cos and this one sine? It's because once I make this one cos, then it's cos multiplied by cos. And for me to choose the correct compound angle, I should choose the one that is for the cosine expansion, because the cosine expansion infuses cos times cos, then sine times sine. But the sine expansion infuses sine times cos, cos times sine. So because I have two cosines multiplied together, then here I should have two sines multiplied together. If I used the sine here, then I was going to use the cosine there if I wanted to alternate them. So now this is the compound expansion for cos, so this should be the cosine of 45 degrees minus x. Remember, if you decide to use the sine expansion, this would be the sine of, you'll be getting, if you decide to use the sine, you'll be getting the sine of 45 degrees plus x. That's what you will get. It will still be correct because this answer is exactly the same as that answer there. Right. We move on, good people. I hope that you are acquiring these skills as we move. Right. Now we want to get into the double angles. We want to get into the double angles, but to get there, we want to use our compound angles. To get there, we want to use our existing knowledge of compound angles. Now, derive the formula for the sine of 2 alpha using compound angles. So we're going to express 2 alpha as compound angle, alpha plus alpha. And then from there, when we expand, this would be the sine of alpha, the cosine of alpha, plus the cosine of alpha, the sine of alpha. So you can see that these are similar terms because the sine of alpha, the cosine of alpha, here you started with the cosine. If you multiply two numbers, multiplication is commutative, so it does not matter which one you start with, which term you start with. I'll just explain commutative property quickly here. 2 times 3 is 6, and 3 times 2 is also 6. That is showing you that multiplication is commutative. It does not matter which one you start with. So here, this one can also be written as sine alpha, cos alpha. So you see, these are like terms. So this becomes 2 sine alpha, cos alpha. So that is how you write down sine 2 alpha. It's given by 2 sine alpha, cos alpha, like that. That's very, very important. So you've derived the formula for the sine of 2 alpha using compound angles. So you can do the same for the cosine of 2 alpha. So the cosine of 2 alpha using compound angles can be written as the cosine of alpha plus alpha, which means this would be cos alpha minus sine alpha, sine alpha. That's how you expand the cosine. That's how you expand the cosine. Now, it's cos minus sine. So now this would be the cosine squared of alpha minus the sine squared of alpha. That would be the cosine of 2 alpha using compound angles. But I will call this equation 1 because once you start having squares, you also can bring in the concept of what? The square identity. We also know that sine squared of alpha plus cos squared of alpha is equals to 1, which means that I can make sine squared of alpha the subject, 1 minus cos squared alpha. I can make cos squared alpha the subject, 1 minus sine squared alpha. So what I'm doing is I'm saying this formula can be written in terms of cosine only. In terms of cosine only, what will I do? Where I see sine, I'll replace the sine squared of alpha with 1 minus the cosine squared of alpha. So I'll get that the cosine of 2 alpha would be the cosine squared of alpha minus 1 minus the cosine squared of alpha. This would be the cosine squared of alpha minus 1 plus the cosine squared of alpha. So this would be 2 cosine squared of alpha minus 1. So we call this one equation 2, because you've expressed the cosine of 2 alpha as a cosine only, as cosine, or in terms of cosine only. Now let's look at this one. We can also express it in terms of sine only. What does it mean? It means from equation 1, cos 2 alpha, which is cos squared alpha minus sine squared alpha, we are going to replace cos squared alpha with what? 1 minus sine squared alpha. We replace cos squared alpha with 1 minus sine squared alpha. So this would be cos squared of alpha is replaced by 1 minus sine squared alpha minus sine squared alpha. So this would be 1 minus 2 sine squared alpha. This is equation 3. So you can see here that there are 3 different equations that can be used to expand the cosine. 1, you can use one that has both the cosine and the sine. 2, you can use one that has been expressed in terms of the cosine only. Or 3, you can use one that has been expressed in terms of the sine only. So because of that, we say that we have 3 formulas, and it's important to know later on in identities that's what you'll be applying. Right. Summary of the formula. This we've covered as the compound expansions, and these are the double expansion. So you can see that the sine of 2 alpha, we've already derived it. You can see that this one is equation 1, equation 2, and equation 3. So that completes or gives the full complement of the compound and the double angle formula that are given in your formula sheet. Right, very, very important. Now, let's move on. Example 7. Express the following as a single trigonometric ratio. Now, if you look at this one, is cos squared minus sine squared. You can see that now it has been derived from, remember, the cosine of 2 alpha has 3 equations. Cos squared alpha minus sine squared alpha. It has 2 cos squared alpha minus 1. It has 1 minus 2 sine squared alpha. So you can see that this is a difference of 2 squares here. So we will know that obviously the cosine squared of y minus the sine squared of y, it means that it's this one. Where is it coming from? It's coming from the fact that I had the cosine of what? 2y, like that. I had the cosine of 2y, just like here. If I have cos squared of theta minus sine squared theta, it means they emanated, or alpha, I mean cos squared of alpha minus sine squared of alpha, it means that they both emanated from the double alpha, like that. So now let's look at the second one. The second one is 2 sine alpha cos alpha. We know to expand the sine, let me write it at the top here, sine 2 alpha is 2 sine alpha cos alpha. So this is given by 2 sine 5 cos 5. So you can see that now, in order to congest this one, 2 sine 5 degrees cos 5 degrees. You can see the alpha is given by 5. So this emanates from what? the sine of 2 times what? 5 degrees. So this is the sine of what? 10 degrees, like that. So 2 sine alpha cos alpha emanates from the sine of 10 degrees. Right, let's look at the third one. Roman figure 3. We have sine alpha minus cos alpha. We have sine alpha minus, sine 15. Sine 15 minus cos 15 times sine 15 plus cos 15. Now here we are going to use the distributive property. We multiply that with FOIL, sine squared of 15, sine 15 cos 15 minus cos 15 sine 15. So this would be minus the cos squared of 15. That's how you're going to FOIL that one. So we still have sine squared minus cos squared. But in the formula, cos of 2 alpha is given by what? Cos squared of alpha minus sine squared of alpha. Ours is sine minus cos, not cos minus sine. So we are going to then take out a negative here, so that this becomes what? Negative sine squared of 15 plus cos squared of 15, because the cosine is the one that should be positive and the sine is negative. So this would be negative cos squared 15 degrees minus sine squared 15 degrees. Then this can be congested to negative cosine of what? 2 times 15 degrees. So this is negative the cosine of 30 degrees. And the cosine of 30 degrees should be square root 2 over 2. Yes. So this is negative square root 3 over 2. Negative square root 3 over 2, because it's a special angle. So that's basically how you simplify that one. You FOIL and then you simplify. Right. Now let us move into these problems that require the use of the Pythagoras theorem without the use of a calculator. It is taking us back to the terminal arms that we did last week. So these are the terminal arms for grade 12, because terminal arms can be done in grade 10, 11, and 12. So in grade 12, we just add compound angles. Right, let's look at the first one. It is given that 13 sine alpha minus 5 is equals to 0. And tan beta is negative 3 over 4, where alpha is trapped between 90 and 270, and beta is trapped between 90 and 270 as well. Determine the cosine of what? Alpha plus beta without using a calculator. So what I'm going to do here is I'll make sine the subject of the formula, sine alpha, and remember they said alpha is an element of 90 degrees to 270 degrees. So now this, if I transpose, I get this as 5 over 13. So I'll first transpose the 5 and then divide both sides by 13, so that I make the sine of alpha the subject of the equation. Making it the subject of the equation would allow me to get the dimensions. So I know that sine obviously is opposite over hypotenuse, or I can refer to that as what? Y over R. However, now we need to find the terminal arm, the quadrant where the terminal arm would lie. We would use the knowledge that we learned last week as well. We're going to check this whole ratio. This ratio is positive. Sine alpha is positive. We locate the quadrants where sine is positive. First and second quadrant. Give the ticks there. And then they said it's between 90 and 270. So when they say between 90 and 270, it means that now they are saying it's either in the second quadrant or in the third quadrant, like that. So we are going to go for the quadrant where we get 2 ticks. So it should be, our terminal arm should be in the second quadrant, like that. Should be in the second quadrant, where this angle here is alpha. And we know that since sine is y over r, it means that our y value is 5, our r is 13. We are left with what? x. So in order for us to find x, would say x would be x in this plus minus the square root of r squared, 13 squared minus 5 squared. So x should be plus minus the square root of 13 squared minus 5 squared, like that. 13 squared minus 5 squared. You get plus minus 12. And then you check in the second quadrant, x here in the second quadrant is negative. So you're going to then say, therefore x is negative 12, because this is existing in the second quadrant. That's where the terminal arm is. So now we can conclude that therefore x of alpha is negative 12. Y of alpha is given by 5, and R of alpha, like that, is given by 13. We've analyzed the first part. Now it's time for us to analyze the second part. The tan beta is negative 3 over 4. Tan beta is negative 3 over 4. Let's first locate the quadrant. Let me do it at the top here, where we also know that beta is trapped between, is an element of also 90 and 270. So now what we need to do is that we need to then work out the quadrants where this can be located. You can see the tangent of beta is negative, and the tangent is negative in the second quadrant as well as the fourth quadrant, because in the third quadrant and the first quadrant it's positive. And then we check, where is this 90 and 270 trapped between 90 and 270? It's in the second quadrant as well as the third quadrant. So we're going to go for the quadrant with 2 ticks. That should be the second quadrant. So our terminal arm also here for beta would lie in the second quadrant, like that, to lie in the second quadrant. But we know that tan is given by opposite over adjacent, which means that it is given by opposite x or y adjacent x, like that, y over x. So we now know that y is given by what? 4, or no, y is 3. Let me check it again. Tan of beta, just want to write it here so that we can clearly see it. Negative 3 over 4, and we know tan is given by opposite over adjacent. Opposite is y over the adjacent, there is x, which means that we associate x with 4 and y with 3. The only trick is now the negative. You need to check in that quadrant which one is negative, because the negative is not for only 3, is for the whole fraction. So you need to decide now which one is negative in the second quadrant. You can see in the second quadrant it's only x that is negative, y is positive. So y would be 3 and x would be negative 4, like that. That's how I decided where this negative should be. And then you have x and y, you need r, so r would be plus the square root. We don't take minus because r cannot be negative. So this would be x, which is 3 squared, plus y, which is negative 4 squared. So this r should be 3 squared plus 4 squared. So this should be a 3, 4, 5 triangle. So r is 5. Therefore, we can conclude x of beta is 3. X of beta is 3. No. It should be a mistake there. Can't be. Let me redraw that one. We are on the second quadrant, like that. X should be negative, so it should be negative 3, and y should be positive, negative 3 and 4. So that's how we decide where to put our negative, because in the second quadrant you can see that x is negative. So that's basically why I said there's an error there. So x of alpha is -3, which means also here I can use my r as the square root of -3 squared plus 4 squared. The result would be the same. X of alpha is -3, y of beta, x of beta is -3, y of beta is 4, and r of beta is equals to 5. Now we want to solve this one, cos alpha plus beta. Allow me to squeeze it in here, cos alpha plus beta. So cos alpha plus beta, this should be the cosine of alpha, the cosine of beta, minus the sine of alpha, the sine of beta. We are using our knowledge of compound expansion. So what is the cosine of alpha? We are going to go to alpha now. Cos is x over r. What is x of beta? -12. R is 13. This you multiply by cos beta. Cos, we are now going to beta. And cos is x over r, so this is -3. R is 5. Minus sine of alpha. We are back to alpha. And sine is y over r. So this would be 5 over 13. Times sine of beta. We are now on beta. And sine is y over r. So this should be 4 over r. R is 5, like that. So we simplify this. 13 times 5, the denominator 13 times 5, that's 65. The numerator -12 times -3, you get 36, minus the denominator is still 65, and this is 20. So 36 minus 20, this should be giving us 26 minus 20, 13 times 5, yes, that's 65, and then 36 minus 20, like that, that should be 16 over 65, like that. So that's what you obtain from simplifying that. You obtain 16 over 65. Right, we move on. We solve problems that involve reduction formulae. Sample 9. Now, if we look at this one, we are going to check 720. 720 is an angle that is greater than 360. So you are going to subtract 360 until you get to an angle that you will manage. So this is sine. You subtract from 720, you subtract 360, you get 360. So this is sine 360 minus 2x. Now, this is in the fourth quadrant, and sine is negative, so this would be negative sine 2x. Divide by the sine of 180 plus. 180 plus is in the third quadrant, and the sine, if we are to write that, all sine theta, tan theta, and cosine theta. Now, in the this is 180 degrees. This is 180 degrees plus x. This is 180 degrees minus x. This is 90 minus x. This is 360 degrees minus x. Now, if you check 180 plus, it's in the third quadrant. And in the third quadrant, sine is negative. But because it is squared, this would work out to be the sine, positive sine squared of x, plus the sine of 90 degrees plus x. 90 plus is in the second quadrant, and sine is positive there. However, it has to change to cos x. And the cosine of 180 plus x. 180 plus x is in the third quadrant, and the cosine is negative there, so this would be negative cosine x. So this would be equals to negative sine 2x divided by sine squared of x minus cosine squared of x. Remember, with our double angles, we have cosine of 2 alpha, which is cos squared of alpha minus sine squared of alpha. So you can see here they started with sine. Sine is positive, so here sine should be negative. It's cos that should be positive. Cos should be positive. So we are going to then use the method that we used last time, minus sine 2x. We factor out a negative, we get cos squared of x minus sine squared of x. Now we move on to this. We get that if we can try to simplify this one, we can get that negative sine 2x divided by cos squared x minus sine squared x. This should be negative cosine of what? 2x. So this will simplify to the tangent of 2x like that. It will simplify to the tangent of 2x. So I was able to actually use also our compound or double angle reduction there. Now, up next is this one. See here. Okay, let me see. Going back again. Okay, we're done with that. This one is also a numerical one. It's a numerical one. So this is a numerical reduction. We can call it just a numerical reduction. With this one, what we need to check is sine 345, sine 255. So here, what we can basically do is we can have that this should be the sine of, because it's 345, we check it's in the fourth quadrant. What is the instruction in the fourth quadrant? 360 minus. What can we subtract from 360 to get to 345? We can just simply subtract what? 360 minus, let me take this out, minus 15. And we know that sine in the fourth quadrant is negative. So this would be minus sine 15. So the solution thereof here would be equals to minus sine 15 times. We have sine 255, sine 255. Let me write it here. Sine 255. We check which quadrant this is in. We should check which quadrant this should be in. It's in the third quadrant. 255 is in the third quadrant. How do we express this in the third quadrant? This should be sine. It's 180 plus. What should we add to 180 to get 255? We should add 75. So this would be the sine of 180 plus 75. And the sine in the third quadrant is negative. So this would be negative sine 75. So this is multiplied by negative sine 75. So multiplying by negatives here, we get sine 15 and then sine 75. Sine 15, sine 75. So we can use, because we know when we work out with our compound angles, when we work with our compound angles, we know that the double angle expansion for sine 2 alpha is 2 sine alpha cos alpha. So this is a product of two sines. And in order to make this look the same as that, what we need to do now is that we are going to express, remember this is sine 75. We express the sine of 75 as a cofunction. So this would be the cosine of what? The cosine of 15, because sine 75 and cos 15 are equal. We wanted to express it in terms of cos so that it becomes a product of sine and cos. But now, having the product of sine and cos without the 2 will not also allow us to be able to simplify. So what we do is we strategically introduce the 2. So it's half times 2 into sine 15 cos 15. Now half times 2 still gives us 1, which takes us back to the original expression. But we know that this part, 2 sine 15 cos 15, gives us what? The sine of what? 2 times 15. That is the double angle. So this would be half the sine of 30. The sine of 30 should also be half. So this would be half times a half. This would be 1/4, like that. So that is how you basically approach that one. Now moving on, because of time, this one we are not going to do it. It's the one that was supposed to be done by you, but because of the time factor, we'll leave it out. It is testing the same skill as the one that we just did. Now I want us to move quickly to identities. What is the strategy in terms of proving identities? You split the left-hand side and the right-hand side. And then you use the basic identity, cos squared of theta plus sine squared of theta is 1. And you use the other basic identity, tan of theta, as the sine of theta divided by the cosine of theta. And then from there you use double and compound angle formulae. That's important. For addition and subtraction of fractions, use the LCD as well as the conjugates. We spoke lengthily about the conjugates last week. Now, when we factorize, please consider taking out the highest common factor, difference of 2 squares, trinomials, grouping, sum and difference of the 2 cubes. And it's also important that you express all the terms in terms of sine and cosine of angles. Also, in addition, wherever you see sine 2 alpha, you always need to change that to 2 sine alpha cos alpha. It's very, very important. Right, let's look at the few examples on identities as we try and conclude today's lesson. Right, let's look at the first one. Prove the identity, the cosine of 2 alpha divided by 1 plus the sine of 2 alpha is the cosine of alpha minus the sine of alpha divided by the cosine of alpha plus the sine of alpha. Now, we know with our identities, we need to isolate the left-hand side and the right-hand side. In this case, you can see on the left-hand side, yes, there's something you can do. You can use the conjugates there. However, it is much easier to start with the left-hand side because you have the double angles. So, and you have your formula sheet and the double angle formula. So, we start there. The left-hand side is equals to, it does not mean, good people, you can't be using the right-hand side. It can be used, but start with the side where you have more work to do, or where you have now what we call double angles and compound angles, if possible. Start with that particular side. The side without the double angles and the compound angles, you leave it at first. You try and simplify the one with the double angles and the compound angles because you know those formulas. So now, if you look at the numerator, it's cos 2 alpha. And cos 2 alpha has 3 formulas. It has cos squared alpha minus sine squared alpha. It has 1 minus 2 sine squared alpha. It has 2 cos squared alpha minus 1. These are 3 formulas. We need to be able to choose one that will actually help us solve the problem. So we are going to have to look at the right-hand side for guidance. If you check on the right-hand side, the numerator has cos and sine. The denominator has cos and sine, which means that this should look the same as that, we know, which tells you that you need to change the cosine, but you change it to have cos as well as sine. That is why I'll be using cos squared alpha minus sine squared alpha. I'm using that simply because on my right hand side, on the numerator, I have both sine and cos. So that gives me a guidance or a guideline. So now, let's look at the denominator. 1 plus 2 sine alpha cos alpha. There's only one way of changing the sign of alpha. Now, here, good people, there's something here that we need to consider. We spoke about it lengthily in our presentation last week. So, on the grade 11 revision, it's important that when you see the number 1, you can also think of it, especially if you are given 2 sine x cos x or 2 sine alpha cos alpha. Think of 1 as what? Sine squared plus cos squared, because we know sine squared of alpha plus cos squared of alpha is equals to 1. And this will help you. It will help you unlock a perfect square trinomial. So we'll write this as the cosine squared of alpha minus the sine squared of alpha. This will help us if I write this as the cosine squared of alpha plus 2 sine alpha cos alpha plus the sine squared of alpha. I can now factorize the numerator. Difference of 2 squares. Cos alpha minus sine alpha into cos alpha plus sine alpha. That is the numerator. The denominator, I can also factorize it. This would be the cosine of alpha plus the sine of alpha into the cosine of alpha plus the sine of alpha. We can actually look at it here. Let's just try to simplify it here. Suppose that we are saying cos alpha is x and sine alpha is y, for argument's sake. This expression would be x squared plus 2xy plus y squared. This is a perfect square trinomial. This is x plus y, x plus y. If you FOIL that, you get x squared plus 2xy plus y squared. So this can be written as x plus y all squared. That is why we are calling it a perfect square trinomial. Now from here, since we've simplified this, we can divide those that should be divided, like this one and that one. They divide out. So you are left with cos alpha minus sine alpha divided by cos alpha plus sine alpha. And this, fortunately, is the same as the right hand side. So you are done proving that identity. But remember, good people, we do not discard the fact that you can use the conjugates here to be able to simplify that one as well. So, but the idea here is that I started with the left hand side because I had double angles, and in the numerator I have cos 2 alpha. The cos 2 alpha, how do I know which formula to choose from the 3? Because it has 3 correct formulas after it has been actually after it has been expanded using compound expansion. You get the 3 formulas for the double angle of the cosine. Now I need to know which one to choose. I know that if the left should be equals to the right, then the numerator on the left should be the same as the numerator on the right. And the numerator on the right has cosine and sine. That is why I chose an equation with cosine and sine. Right. We move on, good people. This is still proving identities. So in this one now, we are going to check the left hand side and the right hand side. You can see more work can be done on the left hand side. More work can be done on the left hand side because it has cos, sine, sine. So this you can see it's a compound angle. So what we can basically do is we can try to congest it. So we can work first on the left hand side. So cos, so this is a compound angle for cos 5 theta minus 3 theta. Divide by cos theta minus sin theta. You see, I was able to reduce or to congest this compound angle because this was in the expanded form, so I'm congesting it. So this gives me cos 2 theta divided by what? Cos theta minus sin theta. You can see when you look at the right hand side that you need both cos and sin. So you will change cos 2 theta into what? Cos squared theta minus sin squared theta. Divide by cos theta minus sin theta, like that. So this would be the cosine of theta, difference of two squares, minus the sine of theta, the cosine of theta, plus the sine of theta, divide by the cosine of theta minus the sine of theta. So these two are going to divide out. You are going to get that the left hand side, if you continue with it here, is given by cos theta plus sin theta, and this fortunately is also equals to the right hand side. Right, good people, that's there, the identity there. Now I have this last one. I think because we've run out of time, I'll just solve this as the last problem for today. I'll solve this as the last example for today. Now looking at the complexity of this, you can see that on the right hand side there is that particular square root. So what we need to do is, we know in order for us to remove any square root, we should have perfect squares. So this should be now a over b, which means for me to remove that square root, I should have what? Perfect squares underneath that square root. Now we're going to have to check how we can find those perfect squares. But first things first, let us work on the left hand side first, because on the left hand side we have complex or we have compound or double angles, I should say. On the left hand side we have double angles, so we will start working with those double angles. So this is 2 cos of x plus 2 sin x cos x over, now I'm having this one, I can simply change this one to 1 or cos squared of x minus 1 plus 1. 2 cos squared of x minus 1 plus 1. So this would be 2 cosine of x as a common factor. I can take out 2 cosine of x as a common factor here. I will get that this would be 1 plus the sine of x. Divide by 2 cos squared x minus 1 plus 1, I get what? 2 cos squared x. So this would be equals to 1 of the cosine squared of x, the 2 and the 2, one of these is going to go. I have 1 plus sine x divided by what? Cos x. I will leave it as it is because I cannot simplify this any further. However, on the right hand side, I have a square root like that, and I want to then make use of what? The conjugate. 1 plus sine x over 1 minus sine x. In order for me to achieve these perfect squares, I can make use of the conjugate. In this case, I decide to say, let me use the conjugate 1 plus sine x over 1 plus sine x, like that. That would be the conjugate that I use. So in the numerator, we are fortunate. We get 1 plus sine x into 1 plus sine x. In the denominator, we get 1 minus sine x times 1 plus sine x. So to simplify this, this would be the square root of, this would be 1 plus sine x all squared, because we are multiplying the same terms together, divide by, this would be 1 minus sine squared of x. If you simplify it, 1 minus sine squared of x. So this still becomes the square root of 1 plus sine x all squared, divide by 1 minus sine squared of x can be written as the cosine squared of x. So you can see now you have a perfect square in your numerator and you have a perfect square in your denominator. So this will ultimately simplify to the square root will then go, because if you have the square root of a squared over b squared, this is the same as the square root of a squared divided by the square root of b squared. We are using the laws of sets. So this would be a over b. So what is the square root of 1 plus sine x squared? It is 1 plus sine x. What is the square root of the cosine x squared? Because cos squared of x can be written as the cosine of x all squared. What is the square root of that? It should be the cosine of x. So now you can see that the left hand side is equals to the right hand side, like that. The left hand side is equals to the right hand side. So basically here you worked with the left hand side where you had compound angles. You simplified until you can no longer simplify, until it was in its simplest form. And then on the right hand side you made use of the concept of what? The conjugate, to say if I have the denominator 1 minus sine x, its conjugate would be 1 plus sine x, like that. Then you simplify and you were able to get those perfect squares, which simplified and give you the left hand side being the same as the right hand side. Right, good people, because of time, the last two examples we will not do them. The last two examples will not cover them. That's because we've run out of time. Now, the summary for this lesson: in order for you to be competent in solving trigonometry problems or working with trigonometry, you should know how to express trig ratios as sides of right angle triangles with respect to a specific angle. You should know and master the cast diagram. That's non-negotiable. You should know and master it, because that is the diagram that you will use to solve all questions in trigonometry. All of them depend on the cast diagram. Now you should know reduction formula, cofunctions, negative angles, and multiple rotations. Also know how to work with those special angles 30, 45, and 60. Very, very important. Understand and know how to prove basic identities. Use the formula sheet to expand compound angles, and also know that the formula will also apply in expanded versions. Equations are true from right to left as well. So it's very important to know how to expand as well as to know how to congest. You need to practice a lot of those problems, because with practice you become better at it. Use a formula sheet to solve problems involving double angles. Remember, formula sheet, the use of formula sheet is important. Please make a formula sheet your friend. Right, good people, thank you very much for tuning in, and please make sure you also tune in next week, where we will be concluding our trigonometry. So thank you very much. Please do take care of yourselves, and please also take care of each other and practice mathematics. Goodbye.